Hello everyone. The topic of this lecture generalize linear least squares and non-linear least squares. In the previous lectures, we talked about the data points. We learned that in the practical situations, the data are mostly given as a data pairs. Some of the data as exact data. When we have exact data, we are doing the interpolations, is meaning we are fitting a function over all the data points, and we have a two category, local interpolation and global interpolations. This is about the exact data. But once we have a noisy data, we are doing the best fit over the noisy data, and one of the method is a least squares. Okay, for the least squares, we have a two category, linear least squares and non-linear least squares. This is the quick review from the previous lectures. Okay, for example, this noisy data is given and we are passing these lines or this linear equation over this noisy data. And as you can see, the order of these functions is significantly less than the number of the data points, okay? Because again, this is as a noisy data, and when we are fitting a function over the noisy data, the number of the coefficients should be much smaller than the number of the data points. We have a different methods for the linear least squares, okay, but in previous lecture, just we are focusing about the polynomial functions. And the polynomial function also considered as a linear least square. The reason is because as you can see, all of these coefficients, no matter what is the order of the polynomial functions, is all of these coefficient is linearly connected together, okay? And look has other methods when we are doing the fitting the function over the data, exact or noisy data. The finding of this coefficient is very important. And for example, first we start by this function. When we are using the first order of the polynomial functions and we are fitting over the noisy data. Based on these linear equations, we have to find the A0 and A1 based on the data points. Okay, the first step, we define the sum of the square of the error and it's shown by SSE. This is the yi, this is our fitting functions, okay? And the SSE is found by these equations. And again, the yi is the data points, and what is the yxi is a function that we are fitting over the data pairs. And this is based on the order of the yxi, okay? We have different coefficients. Okay. Once we write the SSE, the next step, we minimize the SSE respect to the coefficients of the fitting function. For example, our fitting functions, we have two coefficients, A0 and A1, and we minimize the SSE respect to the A0 and A1. After that, we try to rewrite these equations in the format of the matrix and vector. And this is about the A0 and A1 as a two variables that we have to find it. And this is about the matrix that is fine based on the partial derivative of the SSE respect to the A naught and A1. And this is about the right hand side. Now we can say we have two simultaneous linear equations and we can find the A naught and A1. And this is the answer of these fittings. But if you remember, when we are fitting a function, okay, we need to measure it. This fitting, is it good or no? Okay, for this reason, we have some things, okay, like as the correlation coefficients. But before I talk about the correlation coefficients, we learned that when we are using the polynomial functions for fitting over the noisy data for convenience, instead of to write the sum of the xi square, yxi, and the rest, okay, we are using the s notations. Again, this is just for the polynomial functions. And see, we find the A naught and A1 by inverse of this matrix times y times these vectors. Okay, again, how we can check this fitting is good or no? We are using the correlation coefficients, okay, and the correlation coefficient is defined based on the SSD and SSE. The range of the correlation coefficient or R squared between 0 and 1. When the correlation coefficient is close to the 1, is meaning our fitting is very good. But once the R square is approached to the 0, is meaning our fitting is not good and we have to improve it, maybe by increase the order of the function or by changing the functions. Another component is a standard error. The standard error should approach to the 0. Okay. For example, when we solve the problems and the correlation coefficient for numbers for the problems is not close to the 1. The next one of the approach is increase the order of the functions. For example, if we are using the second order of the polynomial functions, okay, that fitting over the noisy data, again, we will do the same process. We write the SSE and as you can see, we have three variables, A naught, A1, and A2. And for finding these three coefficients, we minimize the SSE respect to each of these coefficients. Okay. Then we are trying to rewrite these three equations in the format of the matrix and vector. And this is the vector and okay, now we have this matrix and this is the coefficient that we have to find it. And this is the right hand side, okay? Again, we solve these equations, okay, these three system of the equation by direct method and find these three coefficients. And then we measure the R square and standard error. If you look at the examples in the previous lectures, you can see by increasing the order of the polynomial functions, the conditioning number is increased rapidly. This is one of the issue when we are increase the order of the polynomial functions. Okay, When we increase the orders, okay, again, the system maybe start to wiggles and the conditioning number is increased quickly. For solving this issue, it's better, maybe it's better to try another functions that is not as a polynomial functions. Also, as long as coefficients appear linearly combined, the resulting equations are linear. For example, in the polynomial function, we see the all of the coefficients a0, a1, a2 to the am linearly combines together. For this reason, we have a linear least square. And when we stop the increasing the order of the polynomial function or any or order of other functions, if the fit becomes non-physical and or when the variance of the curve fit approximately equal the variance of the data, is meaning when the SSE approximately equal to the SSD, we stop to increasing the order of the functions. For example, increase the order of the polynomial functions. We can generalize any least square fit for linear combination of the coefficient as this format. AJ is represent the coefficients and phi jx are the functions that we are fitting over our data, and the phi jx is chosen by user, maybe as a polynomials or other functions. For example, our previous examples, we are using the polynomial function for fitting over the noisy data, and we can write the phi jx equal x to the power j minus 1. When the j as a 1, we are fitting a constant value over the noisy data. When the j as a 2, we are fitting a linear polynomial function over the noisy data, and so on. Again, the phi jx is defined by user. And for finding the coefficients, okay, for the phi, the coefficient for the fitting function over the noisy data, again, we write the SSE is a yi is a value of the noisy data, and this is our fitting function, maybe polynomials or any other functions. But the point is the A and all of the coefficients linearly combine together. And depends on how many coefficients we have it, okay, then we minimize the SSE respect to each of the coefficients, okay, and then we rearrange in the matrix format, and this is the matrix, okay, and each component of the matrix is found by these equations, and this is about the right hand side of these equations. And the whole of these equations are called the normal equation of linear least square, and the CJK is called the cofactor matrix. You can try by for polynomial functions, okay, and you can see for example, for matrix 2 by 2, you will get the same answer like as S double X, S sub X, S sub X, and S sub double X, okay, for the matrix. And then we solve the problems. If the chosen set of expansion function is a phi jx is not linearly independent, then the cofactor matrix C will be singular, and because in these equations are not linearly independent. Definitely the matrix of the determinant of the matrix of the coefficient will be 0, and the linear system cannot be solved for coefficients. Okay, this is our fitting functions, and when the value of the j as a 1, as you can see, we are fitting a constant value over the noisy data. When the j as a 2, we have this linear polynomial function. When the j as a 3, we have a quadratic, and this is as a cubic functions. For example, if we are trying to fit the order force of the polynomial function over the noisy data of the previous problems in the lecture 14, we need to find the 5 coefficients: A0, A1, A2, A3, and A4. For this reason, the dimension of this matrix will be 5 by 5. Okay, and we can find the value of each of these elements based on the rules of the S sub x, and so on. And when we try to find the conditioning number of this matrix, as you can see, the conditioning number is now is 3 times 10 to the power 5. This is a very large number, okay? And we can say the system approach to the ill condition if we are increasing the order of the polynomial functions. When we solve these 5 linear system of the equations, this is the value of the coefficients for these polynomial function with order 4. And we check the correlation coefficient. As you can see, the correlation coefficient now is a 0.948, and we can say by increase the order from 3 to the 4, the correlation coefficient from 0.9, I believe 28 is, or 18 is changed to 0.948, is meaning the correlation coefficient is improved, and standard error is reduced to the 0.248. This is about the order force, okay? And see, this is our fittings functions over these noisy data. This is about the general code for linear least squares. We define the cofactors based on these equations. This is about the right-hand side, and we can find the coefficients, okay, based on the inverse of this matrix times B. Again, the phi x is defined by user. For example, for previous examples and in this example, we are using the polynomial functions and for fitting over the noisy data. We find these coefficients. After that, we will check the correlation coefficient and standard error. See, this is the comparison between the linear, quadratic to the quintic polynomial functions that we are fitting over these for the noisy data. Okay, this is about the solutions. Another category for the least square curve fitting is a nonlinear. We have a nonlinear least squares, okay, when the linear least square fails to produce an acceptable fit over the data set, or Another conditions, the physics dictated that the fitted function is nonlinear in coefficients. For example, look at these examples. And we have a mass spring dampers, okay, and the displacement of the mass m is found by these equations. A naught, A1, and A2 and A3, okay, we can say as a coefficient of these functions, okay, and as you can see is non-linearly dependent to each other. And we can find the acceleration of the mass m by take a second 2 times derivative from the displacement of the mass. And this is as a acceleration of the mass of m. We try to get obtain the data from the accelerometer for these problems, okay? And again, we know that the acceleration of the mass m is follow this equation. It means the coefficients are non-linearly dependent to each other. Okay, for nonlinear least square, we have a fitting functions, okay, and same as the problems, okay, same as the previous problems is meaning the mass spring dampers, okay, all the coefficients, okay, are nonlinears. Then we evaluate the SSE like as the linear least square, okay, but in the SSE for nonlinear equations, these functions, okay, the coefficient are non-linearly dependent each other, okay, and the yi is the value of our variables for our data. Then we minimize the SSE respect to the coefficients, okay, and leads to m simultaneous nonlinear equations in coefficients a0, a2 to the am. For example, this is as a general equation of the SSE, the partial derivative of the SSE respect to the AK main coefficients, okay? And now we are solving these nonlinear equations. And if you look at these problems, the A1 and A2 as a coefficient of these problems, we minimize the SSE respect to the A1, okay? This is the yi minus this fitting function over the noisy data, and this part is show the derivative of this function respect to the a1, and this is about the a2. If we are trying to write in the format of the matrix and vector, okay, now we have a two couple nonlinear equations, and we can solve the problems by Newton-Raphson method. And if you remember, for the solving the nonlinear system of equation by Newton-Raphson, we need the initial guess. And after that, once we find the coefficient, then we check the correlation coefficient and standard error for the fitting function over the noisy data. For example, this is as the exact function that we have, okay, and by this function, we are trying to make a noisy data, okay, and we randomly add this noise value, okay, or this random value to this function. Now we have this noisy data, and the problem mentions, okay, we have to fit this function over those noisy data. For finding the A1 and A2 as a coefficient of this problem, as you can see, these two coefficient is connected together, is not connected together linearly. For this reason, we will solve the two nonlinear equations. Okay, we write the SSE and minimize the SSE respect to the A1 and A2. And then we apply the Newton-Raphson method for finding the A1 and A2. Just as a hint, if you remember, for finding the Jacobian matrix in the Newton-Raphson method, we take a partial derivative from the function respect to each of the variables. Okay, for our variables here is A1 and A2. For control and minimize the mathematical operations, and instead of to take a partial derivative from the function, we can use the forward finite difference. Okay, the only things we have to know that what is the step size for the problems. The step size is given here. Okay, delta alpha is like as the delta x. And we can find the value of the Jacobian matrix by forward finite difference. And then we solve the problems. Okay. For the Newton-Raphson method for solving the nonlinear system of equation, we need the initial guess. This initial guess is given. Once we solve the problems, this is the answer of these two coefficients. Okay. When we check the correlation coefficient for these noisy data, based on this fitting, okay, the correlation coefficient is 0.903, okay, and this is a good fittings. See, this is the value of the A1 and this is as a A2. See. If you remember, this is the exact function that we are trying to make a noisy data to produce the noisy data based on this function. This is the A1 and this is the A2. Okay, as you can see, the exact value is a negative 0.5. This is as a negative 0.472. Is very close to the negative 0.5. For this reason, the correlation coefficient is a large number. And this is our fitting function over these noisy data. Again, for these examples, okay, we solved the previous problems, but we changed the initial guess. When we run the Newton-Raphson method, with this initial guess, the value of the A0 and A2, A0 and A1 is changed to the negative 67 and 11. While in the previous examples, in the previous conditions with this initial guess, okay, the value of the A1 is a negative 0.472. Now it's changed to the negative 67, okay? And once we check the correlation coefficient based on these two coefficients, A0 and A1, as you can see, the value of the R square is decreased to the 0.307. Okay, and it show this is not as a good fitting because the R square or correlation coefficient should approach to the 1. This is another examples. Okay, We have A1, A2, A3. Okay, it means we are fitting the y sub t and yt, okay, over the noisy data. And as you can see, we have a nonlinear equations. Okay, we have A1, A2, and A3 as a three coefficient for these problems. We minimize the SSE respect to the A1, A2, and A3. And then we will have a three nonlinear equations, okay, and we solve these three nonlinear equation by Newton-Raphson method, and we need the initial guess for A1, A2, and A3. And again, once we find these three coefficients, we will check the R square or correlation coefficient and standard error. Look at the previous examples. This is the end of this lecture. The quiz 7 will cover all the materials for the chapter 5. It means the fitting function over the exact and noisy data.